excessive wind pressure on it. So the bridge completely started moving. It started having this rocking motion, which increased as the wind increased. And as the amplitude kept increasing, the bridge kept shaking like a pendulum more and more, and eventually just crashed into the river down below. But because it was a very slow buildup, the people had time to actually get off the bridge, and no one really died. So the total death toll was 0 dead and 0 injured, which is very good. But it also makes for a very wonderful a video to see how damage can happen in these kind of bridges. So what is the motivation? Why do we even need something like a structural health monitoring system? As you can see in this slide, I have a few examples of bridges collapsing, where we have some which have no deaths or injuries, some which have a larger death toll. And continuing on, we can also see a few more examples. Now, this also includes a ferry bridge and a walkway collapse in a building, as well as another bridge. So as you can see, there are many disasters involving infrastructure around the world. So what I've selected here are disasters that could have benefited from having a structural health monitoring system. So the other motivation when it comes to having a structural health monitoring system is that it saves money. So the annual cost of damage to infrastructure around the world is $18 billion. And this is only due to natural disasters. And if you look at the overall cost of damage to infrastructure, it's anything between $391 to $647 billion. That's a lot of money. And it's expected that if infrastructure that we build from now on is more resilient and better maintained, we can have savings of about $4.2 trillion. While the expected increase in cost with building these improved or better infrastructure is only 3% of what we're spending right now. So with just 3% of an expenditure, you can expect to save $4.2 trillion. So why do we need structural health monitoring systems? The first one is, as of now, our maintenance programs are time-based, which means that we go and monitor these systems at periodic intervals. So this can be expensive and also time consuming. But if you're using a structural health monitoring system, you can use a condition-based program, which means you can go and examine the system when you find that there is a problem. You don't have to do it just because it's time to do it. And the other thing is, structural health monitoring systems can provide real-time information about the condition of the structure. And the last one is that in case of an extreme event, such as an earthquake or a blast or a typhoon, you can, SHM can give you rapid condition screening, as in it can give you immediate information on what the condition of the structure is right now. But then, the real reason why SHM has gained popularity in our field is because inspecting structures and monitoring structures is really, really hard for the people who are doing the job. So you can see a few pictures of people trying to inspect bridges and structures over here. So you can see some people who have to crawl underneath on the floor, and this guy is wading through a river. This person is preparing to actually go underwater, and these people have to hang off the edge of a dam for hours together just to do some examination. So now if we look at the stakeholders and beneficiaries of a structural health monitoring system, the first one is that it makes infrastructure safer for users. That is, it makes it's safer for the general public, the people who own the buildings, the people who occupy the buildings, and also the people who fund or give money for these buildings. They also save money by increasing the serviceable life of these structures and reduce the maintenance cost. And then the other one is that they give early warnings in case of any issues, which allows the occupants of the building to leave the building before anything happens. And also it gives first responders and emergency services time to to get to the site of disaster as soon as possible. And the other one is that it makes the lives of inspection engineers and regulatory authorities easier. And lastly, as civil engineers, we are obviously responsible for designing, manufacturing, and using these technologies, and also increase awareness about infrastructure safety with the general public. So structural health monitoring has 7 basic axioms, of which we'll be discussing only the first 3. The other 4 are more on data processing, so we'll leave that for now. So let's discuss the first one. So the first one is that what you can see here is a piece of aluminum. It looks like it has no flaws, but when you look at it through a scanning electron microscope, you can see the microscopic flaws that exist in these in this piece of aluminum. And if you zoom in even more, you can see even more damaged pieces in there. So the first one is that all materials have inherent flaws or defects. It means that there are no perfect materials. The second one is that the assessment of damage requires a comparison between 2 system states, which means that you cannot take a structural health monitoring system and then use the data that you get as is. So you have to compare it with the previous state, as in you take 2 readings and then you see how much has changed over that time period. The third one is that existence and location of damage can be identified by just using the measurements, but how bad is this damage, or what kind of damage is there? To find that information, you need to do additional analysis of this data. So here we talk about what are the steps that are involved in a structural health monitoring system. So the first one is you have to identify the structure. Where is this structure located? What is its type? How old is it? What is the material composition? What kind of damage are we expecting? The second one is what kind of a data acquisition system do you want to use? What are the sensors that you want to use? What kind of equipment do you want to use? The next one is how are you going to store, to transfer this data from your acquisition system to your final analysis spot? And where are you going to store it? So is it, are you going to use cables to do it? Are you going to use wireless systems? Things like that. The next one is how do you interpret this data that's been collected? So you have to do a fair amount of statistical analysis and diagnosis. With all of these, you can get the present structural condition of the system. And then you can conduct the same steps later on, a few months later or a few years later, and then you can compare the 2 systems. So we just spoke about damage detection in the previous slide. So what are the stages in damage detection? So the first one is existence. So question 1 is there any damage in the system? And then the next one is, if it is there, where is this damage? And then the next one is, what kind of damage is present in the system? And then the fourth one is, what is the extent of damage, or how bad is this damage? So with this, essentially you can find out how much of useful life remains, because now you know all the information about what kind of damage is on the system. So now we're going to talk about the kinds of damage detection mechanisms that we have. So the first one is active mode, where you have a system with a flaw and you have a transmitter which will send in a signal which bounces off your flaw and is received by a receiver. And then the second system is the passive mode, where you have a system or a infrastructure material and a receiver. And when a flaw is generated or created, it sends a signal to your receiver. So these are the 2 types of damage detection mechanisms that we see in structural health monitoring systems. So the other classification of damage detection mechanisms is destructive evaluation and non-destructive evaluation. So anyone who's ever been to a grocery store knows how to buy okra or lady's finger. So you would essentially break the tip of the lady's finger to see if it's good or bad. So that is destructive evaluation, because once you destroy it, you cannot go back to the material being in its initial state. And an example of non-destructive evaluation is buying watermelons, where you thump the watermelon to see what kind of sound it makes. And if it's good, you buy it, otherwise you leave it. But that's non-destructive, because the next guy can come and thump on the watermelon again. So what are the disadvantages and advantages of destructive and evaluation and non-destructive evaluation? So if you're doing a destructive test, the data applies only to the specimens that were tested, and you cannot reuse the test specimens. In addition, you also require large and expensive equipment. So anyone who's done a test like, say, compressive strength, knows that you need a universal testing machine for that, and that is a large, expensive equipment. But then the advantage of destructive evaluation is they have very high reliability. So whatever values you get are very reliable. And it's also a direct quantitative measure. So you can use your destructive evaluation numbers as is, but you cannot do that with an NDE evaluation though. But the advantages of NDE are that you can do in situ examination. So you can go to the place or where your infrastructure material is and conduct the test at the spot where it is. In addition, you can also reuse the specimens that you have tested, and they can be put in service later on. Most of our NDT equipment is portable, so you can essentially just carry it in your hand like a briefcase and go do your test and come back. NDT is also cost effective in an overall way, because you don't have to extract specimens. You don't need expensive or really large equipment. But the cons of NDE are that the values that you get have a much lower reliability when you compare it to a destructive test. And they're also very dependent on the operator. So it's suggested that whenever you do NDT test, you ask the same person to do the test each time. But also the advantage is that you could use these in places that are hard to reach or that are not accessible. So till now, I've spoken about general motivations as to why structural health monitoring is required. But now I'm going to talk about what my personal motivations were for adopting structural health monitoring. So my research project was on basically, we saw micro cracks in in-service bridge girders. That is, girders that are inactive bridges across the state that I live in. And because of this, there were concerns of loss in service life because of these micro cracks. So our goal was to test these girders for mechanical and durability properties. But now the question is, how do you test these in-service structures? Because you cannot really extract specimens from an actual active bridge, because that would cause problems for the structural integrity. So our solution for that was to use NDE. So the procedure that we followed was selecting specimens. So we had around 14 girders, which we sort of went and examined. So we did NDT on these girders. We took cracking measurements, strain measurements. We did ultrasonic pulse velocity, resistivity, and things like that. And then the next one was we also collected cores. So the picture that you see here is me and my undergraduate research assistant collecting cores. And the next step was to do ultrasonic testing on pre-stressing strands that were undergoing corrosion. And with all of this information, the end result was to find out what's the remaining service life on these structures. So if you're doing destructive evaluation, I'm sure everyone's quite familiar with this. So the way you can do it is you can either extract cores from your existing infrastructure, or you can also cast lab specimens with similar mixed designs. And you can do compressive, tensile, flexural strength, elastic modulus, stiffness damage. And for durability, you can do permeability, diffusion, or volumetric changes, chemical changes, among other things. So you can also do flaw detection. That is, you can see if there are any flaws in your specimens using things like computer tomography, which essentially uses X-rays to digitally cut a specimen open to reveal what's inside. So what you can see here in this picture is a cracked specimen, and the red portions indicates where the crack exactly is in the specimen. You can also use a scanning electron microscope to see what is the surface properties of these of the flaw. Again, a scanning electron microscope essentially uses electrons which are bombarded onto the surface of the specimen, and it's read again to see what's the topography or the chemical makeup of the surface of the specimen. But again, these machines are really large, and they're also very delicate. So you cannot, they have to be placed in places that have no vibration, so they're not portable or mobile. So you have to bring your specimen to where they are, and they're also really small. So your specimens are really, really tiny. So they're around a CT, the computer tomography machine can take in something that's about the size of a core or a standard cylinder. But the SEM can probably just take something that's around 4 or 5 centimeters wide. So again, you cannot do NDT with these. So at this point, I think we'll take a short break and see if there are any questions about anything till now. I can see a few people who are trying to, wave their hands. So I'm going to unmute Veerabhadra Patil.
Yes, madam.
Yeah, please.
Okay.
Yeah, I think you had a question, so you can ask me. Who are trying to, wave their hands. So I'm going to unmute Veerabhadra Patil.
Yeah. Veerbhadra Gowda Patil,
Yeah,
you can talk.
please.
Okay.
Yeah, I think you had a question, so you can ask me. Who are trying to, wave their hands. I'm going to unmute Veerabhadra Patil.
Yeah. Veerbhadra Gowda Patil.
Yeah, I have a question. I have a question for. Hello.
Yeah, please ask.
Yeah, I have a question for madam.
Yeah, carry on.
For initial, when the crack is propagated during setting stage itself, how we can detect through this device, madam?
Yeah, please ask. So I will be talking about some of those detection mechanisms later on in the second half of the presentation. So I think I'm going to ask all the participants to restrict their questions to the material that's already been covered, because I'm going to talk about detecting cracks and things like that in the next half of the session. So I'll, unmute the next person, Mr. Suresh Tripathi. Is that okay?
Madam, I would like to know, how do you do the NDT in a place where you cannot assess, like bridge soffits are there? How do you do the NDT on that? Are you using some scanning or using some drones also for capturing the data? and is using sensors also for capturing it and getting the thing interpolated and having the measurements done?
Yes, I'm also going to talk about that in the next half of the presentation, where I talk about active and passive systems. So if you can access the location where you can actually do the test, you do active testing, where you send a person to go take a test. But if it's in a place that's not accessible, like Sir just said, if it's under a bridge or if it's, say, underwater or inside pipes, what you would do is fit sensors that would continuously give you information, which you collect and then analyze in order to find out if there's any damage.
Like suppose if some bridge
Sir, I think you muted yourself. You're muted again.
Madam, the bridges are there. In the bridge, there will be always a rolling load which will be going on in that. So
Right.
it's basically all the dynamic force loads are coming on that. So in that case, you should have a continuous monitoring of the bridges. So in that, if you are just sending a person and doing, in my opinion, there should be a system in which you should have the devices fit in the bridges, and you should get remotely all the data, and from that data you can analyze the thing, how the structure is behaving completely in the 3D model.
Yeah,
So
that's
that type
there,
of
sir. It's,
things
yeah, it's
will be
there.
more advisable, what I understand, with the SHM which I know in that. So how you are proposing, like you are doing, I would like to understand. Like we had something called digital twinning, in which you know the behavior of the bridge of the similar nature, and you have the data on this itself.
Yeah, those are called integrated bridge monitoring systems. So you have those systems as well. I'm going to be talking about that in a few minutes too.
Like
Where you have,
I'm knowing one of the companies who are in Canada who are very actively involved in this type of bridge monitoring and this one. So, and I'm in connect with them also. So I just wanted to understand what things you are doing, because they are doing in a way like complete sensors are being used. It's a Starmas Canada which is there, which is known to me. They do complete monitoring accordingly. And you don't have to send anyone to the site for getting the data, and all data are created. Only thing is that you have to have a proper data integrity, where the data which is coming should be it should be a perfect data in which you can with which you can capture the things and you can analyze on a platform. So all those things are there, which is in the latest, which are going on in the industry. So
right.
I'll understand, like you are covering those data in the next session. So like, right. Thank you. Thank you very much.
No problem. So I'll unmute the next person, Vijay Atole.
Hello, good morning, madam.
Yes, sir. Yeah.
Ma'am, my question is, you have said that non-destructive testing and destructive testing. Non-destructive testing is less reliable and it is more reliable destructive. So my
Yes.
question is, how can you do that? How much percentage less reliable and more reliable?
So getting a percentage number like that is very difficult, because it really depends on what kind of things you're testing. So if you're trying to do, say, compressive strength or stiffness, then of course your compressive strength test is much more reliable than doing a non-destructive rebound hammer test. I don't have the percentage values off the top of my head, but I can, always look it up and get back in touch with you with that
But
information.
can we say that NDT is means if it is not possible to carry out the destructive testing, then can we rely on the NDT?
You can definitely rely on NDT, but what is generally suggested is that you should not use NDT testing as a quantitative measure. So for example, if you're doing a compression tests, you can get a 35 MPa concrete and you can use that as a quantitative measure that your concrete is 35 MPa. But say you want to do NTT and you want to say calculate ultrasonic pulse velocity, but then the number that you get is very, very dependent on the material properties, how the operator is actually operating the system and things like that. So it's generally advised that NDT is done as a comparative study. So what you do is you do the NDT once and then you do it again after some time or on a material that you already know the properties of. So you can compare it that way. So it's if you do that, you can have a higher reliability with your NDE. Again, if you cannot do a destructive test, you don't really have an option there. You have to go for an NDT test.
Okay, thank you.
No problem. I'm going to unmute the next person. That's Sharvil.
Yes. Hello. Good evening.
Yeah.
My question is related to your research work, as you shown one photograph that you tested on girders, concrete girders, I suppose, which has shown cracks over it. So my question is that in the codes, for example, design codes are there. So it has been specified that, for example, extreme exposure conditions, there have been specified concrete cover to be 75 mm. And when we tend to increase the cover from 75 mm to higher values, for example, 125 mm or so, people or the clients generally have a skepticism that it could cause shrinkage cracks if we increase the cover more than 75 mm. So but on the other hand, if I am increasing the concrete, I get the advantage of increasing the service life in chloride exposure conditions. So how do we kind of balance this criteria that if I'm increasing the cover, I take the risk of shrinkage cracks, but on the other hand, I get an increased service life. So how do we balance this?
So I think first thing there is that there is advice to increase the cover, but there's only a certain extent up to which you can increase the cover. Before it becomes your specimen becomes too big, or your sample becomes too big, or it's too it becomes expensive to do it as well. So it's generally, if you're going to put your specimen in a chloride rich environment, say you want to put it in a marine environment or on a coastal environment, you would want to be more conservative and add more cover or make your concrete more durable. But again, if you're going to just put your bridge in the middle of the city, it's fine to not really have that much cover because you don't have to worry so much about chloride diffusion there, right? So it all depends on where you're going to put your structure in. So it would be highly dependent on the location of your structure. And also, again, what your client also wants. So if they're more interested in saving money, then you would say, okay, put a smaller cover or, go for that route. Or if your client says, no, I want 100-year service life, then you would go and increase the cover of your concrete. So my research specifically for us, the problem was that these cracks sort of appear later on, around 1 year after these specimens are cast, and they're already in service by that point. So for us, redoing the specimens is not an option at all.
I understand. Okay. Just one more thing I would like to add. So regarding the previous question asked by Mr. Vijay Atole, so he said that there is some percentage of reliability for some test. He asked that question, right? So I just, because my company, it is called Infrastructure Risk Management. We are based in Mumbai. So even I have done my PhD, and this is my startup company. So I would like to kind of throw some light on this percentage of reliability, kind of, not exactly in terms of percentage, but what I would like to add is that even FEMA 365, it says that you can do NDT, but NDT alone cannot be standing alone. It has to be supplemented by concrete coring. So that even the FEMA code says that coring is irreplaceable by NDT. So that is the first thing. Second thing is in terms of the reliability. So first of all, from cores, you can get the direct compressive strength, whereas from NDT, you don't get it. Although you can say that rebound hammer can give you some values of surface hardness, but again, it is affected by carbonation. So again, it is unreliable. But what we have recently done in one hospital project, which we got. So in that, what we did, we actually calibrated the NDTs with in situ strength, and then use that calibration values to get a relative of strength in terms of the NDTs. So that if you are able to calibrate your NDTs, then the question of percentage reliability can be completely eliminated, and you can use your NDT at a more extensive premise of the structure rather than having very little NDTs and very little concrete cores. So that is what I would like to add.
Yeah, I completely agree with that. That using just NDT on its own is not advisable at all. So you definitely want to supplement it with destructive testing values.
Yes, and even if you
so
adopt,
I'm gonna go. Yeah.
Yeah, if you adopt the Bayesian technology, Bayesian inference for using a probabilistic analysis of concrete strength, then it will be actually realistic value, realistic estimation of concrete strength.
Right. So again, you have to compare it with a destructive test to actually get that comparative value at all.
Yes.
So
Yes.
I'm just going to go back to the presentation, and we can continue the question answer session at the end of the presentation. So I hope everyone can see the screen again.
Yeah, Savita,
Okay.
yes.
Yeah, so I'll continue now.
Carry on.
So now we've discussed about destructive testing till now. So what we're going to talk about now is non-destructive evaluation, or NDE. So NDE is generally used to detect flaws in a material. So this flaw can be cracks, improper filling, or segregation of concrete in the field. So I'm a concrete engineer, so most of what I talk about, I tend to focus it all onto concrete. But the same methods can also be used for metals, polymers, wood, and other building materials as well. So essentially, you can take a sample and then conduct tests on them. But if you cannot access this, or if you cannot extract a specimen, or if you cannot access this, the material, then you can always use NDE. So that is, first one was detection of flaws. The next one is dimensional measurements to see what are the dimensions of a specimen. And then the next one is estimation of mechanical and durability properties. So mechanical properties can be strength, stiffness, durability can be resistivity or diffusion. And you can also do strain measurements to see how much, what is the change in strain over time with fatigue loading or impact loading. And you can also do dynamic response measurements. Basically, what is the change in strain when you have applied stress? Say you have a bridge, and if a truck goes over the bridge, what is the change in strain because of that truck? So we'll be discussing these methods in detail in the presentation. So these are the commonly used NDE methods that we will be talking about. So the first one is visual inspection, followed by magnetic testing, infrared thermography, ultrasonic testing, impact echo methods, acoustic emission, and corrosion mapping. So the first one is visual inspection. So this one is the cheapest and the easiest method that's available, because all you have to do is go and look at your specimen. But again, there are also equipment that we can use to do this. So we have things like robotic crawlers, crack microscopes. We also have borescopes, which are basically tiny cameras that are mounted onto wires or cables that you can run through pipes or ducts or wire ducts to essentially see what it's like inside. And obviously we have things like the, crack monitoring systems. We can also use visual inspection for things like pipelines, railway lines, pavements, and marine structures. So what we see here in this picture is a typical visual inspection of a railway line. Again, we also have equipment that does this job. So it's tiny little thing, just runs on these rails and just looks at all the defects in the rails and lets you know if anything needs to be changed. But again, with visual inspection, it's very qualitative rather than quantitative. So it really depends on what your observer is seeing. In addition, you also can't look at things that are, say, buried or are inaccessible or are dangerous to access. So what I have here is a picture of my undergraduate assistant demonstrating how to use the crack microscope. So you can see what a crack would look like, and also see what the width of these cracks would be using just a simple crack microscope. You can take it to the field and do your measurements right there. The next one we're talking about is magnetic testing. So this one, the procedure is really simple. So what you do is you take your part, you magnetize it, and then you add dyed iron particles. So these particles are now attracted to the magnetic flux in this material and will sit into cracks and damage spaces. And when you put a special kind of lighting, you can see the cracks that are visualized. So this GIF here shows the procedure and how these magnetic field lines are shown. So this method is specific, can be used only for ferromagnetic materials such as iron, nickel, cobalt, and some of their alloys. And it can also be used only to detect surface or very shallow subsurface cracks in iron kind of materials. It's typically used in crack mapping of steel structures like bolts, anchors, plates, trusses, etc. Again, it's used in both quality control as well as for inspection of in-situ systems. So you can essentially test a bolt or a plate and then send it in service because this is an NDE test. The next one is infrared thermography. Basically, it's a thermal imager that just detects infrared energy that's emitted from an object. So it converts the infrared energy into temperature and then displays this image of temperature distribution. Most recently, infrared thermography is used in detecting body temperatures of people who are suspected of having COVID-19. That's a COVID fun fact for you. The other one, in civil engineering specifically, we use it to detect delaminations because heat flow through a void or air is slower than through solid concrete. So essentially you can see where delaminations are there. What you see here, the darker redder, the red patches lines are the portions where the masonry has gotten delaminated. Similarly, you can also see the dark red patches here that show delamination in a pavement. They're also used to detect how full silos, fuel tanks, and water tanks, etc. are. You can see in this picture where you can see that till where the material is in the cement silo, it's a darker color than the empty portions of the silo. Another place infrared thermography is commonly used is in defense reconnaissance missions. So you can kind of see the heat signatures from things that were previously there. So you can, find out if there was an object that has been moved because you can still see the heat signature from something that was previously there. And then you can also see the amount of fuel in these aircraft wings right there through your infrared thermography. The other place where you also use infrared thermography is to detect targets when you're trying to, say, bomb a place or shoot someone. The next one is ultrasonic testing. So ultrasonic testing is basically you introduce a high frequency sound wave into a material and then record the time that's taken by these waves to travel through the material. Basically, velocity is distance by time. So you can use it for dimensional measurements. So say you have a concrete specimen, you have a transmitter, which will send out a pulse, and then that bounces off the edge of the concrete specimen and will be received. Now, say you have a flaw in the same system. When your transmitter sends its pulse out, it will bounce off the flaw rather than the edge of the specimen and come back to the receiver. So the difference in the two Ds or the two distances will give you different velocities. So a higher velocity is better than a lower velocity. So that's where you use it for dimensional measurements and flaw detection. So the next one is you can also do material characterization. What this GIF shows is that a solid material, a sound wave will travel faster through a solid material than it does through liquid or gas. So the denser your material, the faster your wave. So a higher ultrasonic pulse velocity is considered to be better because your material is denser or has lesser flaws. The other thing is ultrasonic pulse velocity has been shown to correlate very well with stiffness measurements. So if you are not able to do your modulus of elasticity test, or you don't have enough specimens to do it, you can use ultrasonic pulse velocity to sort of get an idea of what kind of stiffness is expected from the specimen. Again, like with any other NDE, the ultrasonic method is very susceptible to user error, and it's also very difficult to replicate. You get the same person to do it each time. So we also discussed the first method. So there's also an additional, another method that you can use the ultrasonic pulse velocity when you have access to both faces of a specimen. So when you do that, you can also use your system that way to see, just have the transmitter send its pulse and receiver at the other end to calculate the velocity. So these two graphs show the change in cracking and the change in ultrasonic pulse velocity with increased weathering cycles. So you can see that the change in cracking as well as the change in ultrasonic pulse velocity correlate quite well for all of these specimens. And obviously they increase with increasing number of weathering cycles. So it just does go to show that ultrasonic pulse velocity gives you pretty good results when you're trying to look at damage or flaw detection in materials. So this is another way of using the ultrasonic method, pulse velocity method. So what we have here is a water tank with salt water in it and a steel strand that's going through. Our goal was to force this strand to undergo accelerated corrosion and then run an ultrasonic pulse through this strand and measure the change in stress because of the loss of stress in due to corrosion, and also calculate the stress using stress and strain, and then compare the two methods. So what we see here is the sample before corrosion and after corrosion. So once the fracture happens, you have the outer strands just disassembling and the central strand is still there. So what we see here is the change in stress of the uncorroded and a corroded strand. So you can see that the stress in the corroded strand keeps increasing till it actually reaches the fracture point, while the uncorroded segment really doesn't have that behavior. This also shows the comparison of the actual measured stress using stress and strain, and also the stress that's estimated using the ultrasonic pulse velocity. So the white dots are the estimated values and the black dots are the measured values. So you can see that with a statistical analysis of 95% probability confidence level, it does have a similar trend towards the measured stress values. So it does show that you can use ultrasonic pulse velocity to gauge extent of corrosion in pre-stressing strands. So the next method is impact echo. Again, impact echo is similar to ultrasonic pulse velocity, except that instead of using an ultrasonic pulse, an impact is generated using a sound wave. So you have, think of it as like a knee-jerk test where you knock something in order to get a response. So this impact echo method is generally used in bulk concrete structures, whereas the ultrasonic pulse velocity method is generally used in smaller samples. So the ultrasonic, the impact echo method essentially involves a source that will generate a pulse through your sample and you receive it. So what you'll get is a graph that's something similar to this. Now, if you have a flaw in the system, when you have your source, it will generate a pulse, which will hit the receiver, and you get a graph like this. But there is also some leakage of this, the source pulse that comes down, which will hit the end of your specimen and go back. So you get this curve as well. So you will get a modulated curve that looks like this, which is smaller than what you would expect for a system that does not have any flaws. Now, assuming your flaw was extended throughout the specimen, you would have just the source wave hitting the flaw and bouncing back to the receiver. So you'd have a much smaller amplitude when you compare it to the undamaged specimen. So essentially you can detect what kind of flaw you have, how big your flaw is, using the impact echo method. The next one we're going to talk about is acoustic emissions. So essentially when a structure is subjected to an external load, it will trigger a release of energy. So what I have here in this GIF here is a simulation of an earthquake. So anyone who's ever experienced an earthquake will know that the earth essentially releases an acoustic pulse or a sound wave, which is detected by the seismic sensor, which will let you know what the intensity of the earthquake was and where it originated from. So something similar is what we use in acoustic emission testing. So you have a sample and you apply a load on it, which creates a flaw in your material or a crack, which will essentially send a pulse out to your sensor. So acoustic emission is more of a passive test because once you have a flaw, it will send out a pulse which goes to the sensor. So what we have here is an example of an acoustic emission testing for predicting cracking in concrete. So we have a concrete block which is subjected to accelerated corrosion again, and we attached acoustic sensors to the end of each of these samples onto the concrete sample and just let it run. So when the concrete does crack, it'll release an acoustic pulse, which is picked up by the sensor and stored in the data transmission system. So what we have here is how cracking progresses in a concrete specimen. So say you have your strand, and once the chlorides start penetrating, you have a crack initiation, followed by the crack extending all the way to the surface. So when we look at the acoustic emission activity in this, so till there's no corrosion, you have very, very less acoustic activity. And once the chlorides start to penetrate, and then the time to cracking starts, you start seeing small amounts of increase in the acoustic activity. And similarly, as the cracks increase, you have a much higher acoustic emission activity. So this graph shows a clearer picture of what that would look like. So the black line is the cumulative energy, while the white dots are the number of hits or the number of acoustic emission activities that happen. So when we plot this material, you can easily see where corrosion starts from once the activity starts to pick up. And once the cracking propagates, you can see that it starts to hike up quite quite prominently. So you can kind of predict when cracking will start using this acoustic activity. It's more of a passive test now because you just fit the sensor on your material and wait for it to crack. The other place where NDT is gaining a lot of traction is in corrosion mapping. So earlier we had to use the half cell potential measurement, which needs connection to the rebar. So you have to drill a hole in your concrete specimen and then attach a wire to the rebar itself and then take your measurements. But with the new resistivity meters, you don't need to do that. Essentially, it just measures the voltage of your pore solution or the surface pore solution to calculate how the if the rebar is corroding. So if you look at the graph of a non-corroding bar versus a corroding bar, you can see that the voltage is much higher when we compare it to a non-corroding bar. So it's generally used to detect the corrosion in reinforcement and measurement of corrosion rate in concrete structures, in situ electrical resistivity. So till now, we've been talking about passive systems, active systems. So now we'll talk about passive systems. So these generally involve embedding structures, sensors in infrastructure and continuously taking measurements. So these sensors can either be embedded inside the system during manufacture, or they can be attached to the surface later on. And these measurements are statistically processed to find out at what point damage occurs, and if it does, what kind of damage happened. So when we embed these sensors inside the systems, we tend to have nearly a 50% loss, which means that these sensors are very delicate pieces of machinery and they're really small, and they kind of tend to get dislodged during the manufacture process. So anyone who's ever been to a construction site knows that when they're pouring concrete or attaching rebar, it's not like they're going to be very careful with it. They'll just pour it. So these sensors need to be handled with care. So they tend to have a high loss rate. They can also get destroyed during placing or after placing as well. They also have to survive in highly corrosive alkaline pore solution type situations. And again, the other problem is that since they're embedded inside, they also have to be powered some way. So you cannot use solar power to power something that's already inside. So they can kind of run out of power over time as well. So those cons of embedding sensors can be dealt with by using these attached sensors to the surface of the structure. However, there are certain limitations when you use that, because the data that's obtained from the surface is not as reliable or as true as the embedded sensors. So it's generally advised that you use a mix of embedded sensors and surface sensors and active NDT, as well as destructive tests, to actually get a true estimation of the present condition of the structure. So when we talk about goals, or specifically when we talk about passive structural health monitoring systems, the first one is to verify the design assumptions and parameters. That is, we want to see if the structure is performing as it was intended to perform. The next one is sound out an alarm if there is any kind of abnormal loading or response to the abnormal loading. The next one is to see if the structure still has structural integrity after any disaster or extreme event happens. The next one is to issue an early warning if there is any problem. So, before it gets to a really bad state, we can catch the problem early on. And the next one is to essentially improve the design of future structures in the future, so make them better. So this is an example of an integrated bridge management system. So I'm just talking about bridges here, but we can install similar systems on bridges, on high-rise structures, dams, reactors, pavements, you name it, and you can install a structural health monitoring system. I'm just going to use bridges here as an example. So these passive detection systems are broadly divided into sensors to monitor weather, seismic activity, deflection, and corrosion of steel elements. That generally you would go for a passive damage detection system in really large structures where doing any kind of active monitoring would be difficult or time consuming, or it's not accessible. So the first set of sensors that we generally tend to see are weather monitoring sensors. So these are really important where in places where you can see typhoons, hurricanes, or heavy winds are expected, such as in coastal or marine structures. So you have things like anemometers, which measure wind speed. We have thermocouples, which will measure the ambient temperature or internal concrete temperature. So these thermocouples are generally used to prevent issues like alkali silica reaction or delayed ettringite formation, which are sensitive to temperature. We also have barometers, which measure atmospheric pressure, hygrometers, which measure humidity of air, rainfall gauges. Essentially, the goal is to get a clear picture of what kind of environment this structure is under. The next set of sensors are seismic monitoring sensors. So we have things like accelerometers or buffer sensors or acoustic emission sensors, which essentially measure vibrations in the system from external loads like wind or seismic activity or heavy traffic running over the bridge or something of that sort. The other one is bearing sensors, which are attached to bridge bearings or bearing plates in buildings that measure temperature changes in these bearing plates and buffers to see if the bearings are actually still functional or not. The next set of sensors are used to monitor deflection. So we have static strain gauges, which measure volumetric change. So all of us are quite familiar with this strain gauge right here. But on an NDT sensor would be something like this, which is a piezoelectric sensor. The next one is a global positioning system, which essentially measures the change in position of fixed point on the structures. So it helps you see if the point that we've fixed has moved beyond what the allowable amount of movement is. And the next one is we have dynamic weigh in motion sensors, which essentially sees how many vehicles have gone and what was the load of each vehicle. And we have dynamic strain gauges, which measure the deflection due to this dynamic load. And you have tilt meters, which measure the change in elevation. So these things, your tilt meter can be used to see if there's any sinking foundations or shrinkage or expansion in columns, or if there is any sinking of bearing piles or piers or something like that. So now that we have all of this data, the next set is what do you do with this data? So we have things like data loggers, which will collect all this data and keep it. And then the next one is data storage stations. So the loggers will transmit the data to the storage stations. And then we have data transmitters, which will send this data to wherever the analysis people are. And then the next set of people will essentially analyze this data, go through a statistical analysis, and find out if there are any issues. With all of this, essentially you can get the real-time condition of a structure. If you guys remember, I spoke about a bridge in Malaysia earlier on, which collapsed and killed around 30 people and injured around 1,000 people. The same bridge was rebuilt and outfitted with a structural health monitoring system recently. And the new bridge essentially is a box bridge with cable connections. And for this bridge, the main concerns were earthquake and corrosion of the piers. So it has nearly 3,000 sensors of different kinds across the the whole bridge. So I just wanted to show you guys that things can change. A bridge that collapsed earlier can be rebuilt with a new system to be safer. The other one is the Singma Bridge in Hong Kong. Now, this is a double-decker bridge, which is a pretty rare thing. And it's also the largest suspension bridge of this type. The problem with this bridge is it's on the coast, so it suffers through severe typhoons multiple times a year, which means there are heavy lateral winds blowing on this bridge. So this bridge uses a specific SHM called the Wind and Structural Monitoring System, which was designed specifically for coastal structures. So it focuses more on weather monitoring and deflection measurements. So just to summarize, structural health monitoring systems essentially aim to keep structures in an operable condition for as long as they can by observing the current state. So they help save human lives, reduce maintenance costs, increase the service life of infrastructure systems. Essentially, they make the lives of maintenance engineers and inspectors a little easy. And the other thing is these technologies are available and they are constantly evolving and new products are released every day. So as civil engineers, it's our job to keep track of these things and see how we can use them in our systems. Before I end this presentation, I just wanted to leave everyone with this single infographic. If you know, there is, it's expected that by 2025, the market share of integrated bridge systems is expected to increase to 8.8 billion from the 7 billion that it was last year, with Asia Pacific areas contributing to nearly 50% of this growth. So India should definitely look at investing in the design, manufacture, and use these sensors in our infrastructure to make it better and safer for everybody. So these are just some resource materials that you can look at to get some more information on structural health monitoring systems. The first one is a journal that's dedicated only to structural health monitoring. So it has information on what's coming new, what are the tests that are done, field studies, and things like that. The second one is explains what are the fundamental axioms of structural health monitoring. So if you were interested in the 7 axioms, I would suggest looking through this paper. The next one gives us an idea of the history of structural health monitoring systems. And of course, I've also used material from my classes and from my own experiences as well. So I'd like to end this presentation with thanking everybody who's attended today, and also to Jain Institute for giving me this opportunity. And I will give the floor back to Dr. Patil now. Dr. Patil?
Hello?
Yeah.
Yeah, I can hear you.
Yes, sir. So I think we can start the next question answer session.
Yeah. So I request participants to ask the questions one by one. So there are, okay, they have raised the hand. First, I would like to ask Mantesh. Yeah, speak on.
Yeah, I've unmuted Mahantesh Kanti, so they can ask me a question. Hello? I think I'll move on to the next person. That is Sudeep Pradhan.
Yes, good morning, ma'am.
Yeah.
Ma'am, I have a question that how far this technology has been going on for the check of foundation through entity? That's my main question. And how is that reliable in terms of current market?
In terms of?
In terms of our technological and um, like in terms of seismological analysis.
In terms of seismology, it's been used quite extensively because, you know, NDT is literally the only way you can detect seismic activity in the earth. So that way it's exclusively used by seismologists. As far as if you're thinking about foundations, I'm not very sure about what the market share would be for that. I don't really have that information on hand. But they're definitely used in looking at seismic activity on buildings. Like, say, if you, in places like Japan, which experience a lot of earthquakes, they have specific earthquake-proof designs for their bearing plates, right, and on foundations. So they're used extensively in those places. Japan actually is one of the largest markets for seismic NDT methods. So yeah, in foundations they are used, but I don't have a market value for it though.
Is it practicable to use that or not? I think yes.
Is it effective? It is
Yes,
definitely effective because things like acoustic emission sensors are very reliable. They might not be reliable if you're trying to see if there's a crack in concrete, but for something like seismic activity, they're very, very reliable because they're built specifically to extract acoustic data from sound waves. So they're pretty reliable when it comes to detecting vibrations in systems.
Okay, thank you, ma'am.
No problem. I can unmute the next person, which is Subhash Kumar.
Hello.
Yeah.
Yeah. Good morning, madam. Madam, actually, I have to know that whatever NDT we are using in post-tension girder and all the things, very difficult to correlate that graph whether it is unflow, because in earlier stage cracks are very minute, but during service life of period and whatever relaxation of stands, cracks means get larger or wider. Cracks whatever girder induced cracks are, but we can't use in destructive method now, because where rebar is there, where stands are there, ground penetrating radar data is also not too much, and drawings are, so how only NDT and NDT also not reliable authentic, means how the taste is there, person to person vary and all the things, how we will be minimize this type of thing?
So, of course, there are issues with any kind of detection system. Those issues are not, exclusive to NDT. Even destructive testing, if the person who's doing it doesn't do it right, they can give you wrong information. So it's more of how well you do your testing and how much quality control is there when it comes to the testing. For example, when we did ultrasonic pulse velocity measurements on these girders, we had to take readings every year. So I was the person who was taking the readings, because if I asked someone else to do it, our readings were going way off. So what you want to do is you want to be very sure about, make sure that you're taking the readings at the exact same spot and have the same, amount of saturation or moisture saturation in these places. So as long as you maintain enough quality control during the testing process, you should be able to get enough reliable data. again, you should not be trusting just your NDT measurements at all. You do want to use destructive testing to sort of correlate your NDT and destructive tests to get information.
Okay,
Yeah,
thank you, madam. But destructive testing we can't use in post tension and all the things because various stents are there. If they cut, then relaxation will be there and stress loss will be there. Okay, thank you.
So like I said, again, if you cannot do it, you can always do, if you cannot extract a specimen from your sample, you can cast a sample in your lab using a similar mixed design.
Similar mixed design.
And you can use that sample as your comparative sample, or you can cast your own specimen. You can cast like a mini girder or whatever, and you can use that.
Okay. Okay. Thank you. Thank you, madam. Thank you,
Yeah.
Savita madam?
Yes, sir. Yeah.
Yeah, there are a few questions in YouTube also. Okay, one of our Dr. Sridhar sir is asking, what is the new development in fracture mechanics of steel or any metal?
Fracture mechanics of metals?
Yeah, fracture mechanics of steel or any metal.
You would be using nearly the same methods for most of the things. So like I said, you can use magnetic testing to see if, specific to metals and steels, you can use magnetic testing to see if there are any flaws in your system. Or you can also use ultrasonic pulse velocity or impact echo method. And essentially you can use NDT interchangeably between materials.
Yeah, another question. How to combine results from different NDT data sets to obtain higher reliability?
That question is probably really hard to answer on a session like this, because that involves a lot of mathematical analysis and statistical analysis, and that would be very specific on what is your data, right?
Okay.
Again, I'm also not exactly an expert on these things. I am a learner as well, so I cannot really give any advice on how to analyze your data unless I have actually researched this data myself.
Yes, fine. Any other questions from the Zoom? You can ask them.
Yeah, I can unmute the next person, which is Sumit Kumar.
Yes.
Hello, ma'am.
Yeah.
Ma'am, I have a question regarding of DT.
Regarding, sorry, what was that? Could you repeat your question, Mr. Kumar?
Okay, go for the next question, madam.
Okay, I'm going to unmute Niranjan Vaichal now.
Yeah.
I have a separate question here.
Yes, yeah.
The question is now whether NDT is being mandatory for all the structures by the government, and second, will it be mandatory for the for all the public structures to make the health monitoring systems?
As of now, there is no government regulation on use of NDT methods. Frankly speaking, there's not a lot of regulation on NDT itself. It's not like there are a lot of codes or references that you can use. Probably the most commonly used ones are ultrasonic pulse velocity and resistivity.
Okay.
Suppose those are the only codes that we have, and even those are not government regulated, or they're not compulsory on structures. Most of these passive systems that we have, like integrated bridge management systems, they're just implemented by the people who are building it. That's it. It's not government mandated at all.
Thank you. Thanks a lot. Sure. Thank you.
But since you bring that up, it would be a good idea for governments across the world to actually start implementing these programs in government infrastructure, because it definitely will save money and save lives of a lot of people. So, it might be a good thing for civil engineers and designers to start, putting pressure on governments to start regulating these industries as well.
Yes. Thanks a lot. Thank you. Thank you for answering.
No problem. Now unmute the next person, which is Pradeep Sinha Thakur. I think he's not available. So I'm going to unmute the next person, which is Gopi Krishna.
Yeah, hello.
Yeah.
Hi, Sarita. How are you?
I'm good, sir. Thank you.
Yeah, this is Gopi. Actually, I'm from Muscat, Oman. Previously, I had experience in high-rise buildings.
Mm-hmm.
So coming to the last candidate Subhash, including same question. See, actually, these things need very skill. People need skillness, and also main thing while using the sensors in the concrete. How you last slide you explained that there may be people don't know about the sensor importance. When you install the sensors in the concrete, they may pour as it is, and the protection is very much necessary. So there is no question for me. The what you have been given this webinar is very good, informative. The only thing I just I want to pinpoint on the skills and things people to know surroundings. These training people should have at least, because how you told that you cannot rely on anybody and you will go and check. So same way I was also checking in the high-rise buildings. So people need the expertise. And also I agree with you that all should be trained. Without knowing, without training, so whatever we are doing, the data which is not coming proper way is of no use. So what do you say?
Right. So that is very true. So there is a lack of knowledge, everywhere. It's not just that the lack of knowledge is focused in India or anything. It's there throughout the world. And the number of people who are familiar with these systems is very less. And it's also not an
believing on somebody
easy
is very
field.
difficult to on these data actually.
Yeah, it's just a difficult field to get into, because people who know a little bit about everything, like someone like me, it's easy for me to sit here and say things like that. But people who work specifically with these instruments or with one particular instrument know that there are a lot of issues that can come up with this. So yeah, there definitely needs to be specific training on these, and a lot more research also needs to be done to see.
It was good, Savita. It was good, very good, informative for us to see all this new equipment, everything. Thanks a lot.
Thank you so much, sir. Thank you. I will unmute the next person, which is Binayak Samantha. Samantha, probably, sorry.
Yes, good morning, ma'am.
Hi.
Hello.
Yes, please, yeah.
Yeah, my question is, can you explain about pile integrity test and what result it will says to us?
What test, sorry, what was that?
Pile integrity test.
I'm not very sure. Can you repeat that again?
No, I have seen in my site that they use a pile integrity test in the pile after casting the pile. After 10 to 12 days, they use a entity test called the pile integrity test.
Mm-hmm.
So, what result they actually say?
I am not familiar with this test. I'm sorry, so I cannot really speak about it. But you can always look it up, and you should be able to find information on this. I really don't know anything about this. Sorry.
Okay. Thank you.
No problem. I'll unmute the next person, which is Karthik J.
Hello, madam. My name is Karthik. Actually, I was doing some journal paper on fragility analysis. So I'm done my project on in the MTech regarding the same. So I did with the help of SAP software, took a live building, and I was somehow managed to take the fragility curve. So can you please explain me anything regarding this fragility analysis? Is it booming in the industry right now? Is it? I'm planning to take it as my PhD topic also. So
By frigidity analysis, are you talking about freeze-thaw mechanisms?
yes.
Yeah, so there is a big market for freeze-thaw mechanisms. You know, anywhere you go to a cold place, you have to work with freeze-thaw. So that is something that has a lot of market potential. So if you're looking at research in that field, you can definitely do it.
So is it worth it to be in that particular field for this one? Because it also comes under structural health monitoring itself.
Freeze-thaw, I think there is a lot more to it than just structural health monitoring, right? Because you know, freeze-thaw is there in terms of pavements and you know, any external structures, bridges and things like that. So yeah, freeze-thaw has a lot of market potential in terms of research and job opportunities.
Okay.
Any place that's cold has to deal with it. So, you know, it's a good field if you're interested in it.
Thank you.
The next person I'm going to unmute is Mohammed Mullah.
Hello, ma'am.
Hello.
Ma'am, I'm a student of Jain College of Engineering and Technology, Hubli. I'm a final year student. My question is that you told about the structural health monitoring system. It is helpful. Is it helpful for the old buildings or like monumental buildings like Taj Mahal or etc. for the improvement of their lifespan?
Yes, because you know, you don't really want to break or like extract specimens from heritage buildings. So NDT is definitely used quite often in rehabilitation as well as repair of those heritage kind of buildings. Yeah, there's a lot of market potential for that too. It's used quite often there.
And another question is, ma'am, is this COVID-19 will affect the market of this structural health monitoring system?
COVID-19 is going to hit the market for everything. You know, anything that's there right now is going to get hit by COVID-19. And you know, this is not I'm not an economist or you know, a market expert or anything, but just from looking at how things are, yes, it's definitely going to take a hit. But again, you can also think of it as, you know, COVID-19 is something that happens and it's going to go away at some point. So once it goes away, again, people will start developing things. It's not like everyone can stay at home all the time. You'll have to drive on a bridge at some point. So it will definitely come back at some, eventually.
Thank you, ma'am.
No problem. The next person I'm going to unmute is Dr. Nitin Kumar.
Hello.
Yes, sir. Yeah.
Yeah, good morning. This is Dr. Nitin. Thank you for very nice informative session. I only had a small query, like most of the NDT methods are giving qualitative results, isn't it? So do we have any methods we can that we can be used for quantifying those results which we get from NDT methods?
Eventually, yes. So what you would do with your NDT results is comparative to quantitative destructive tests. So you can quantify your NDE measurements as well. Also, you can use if you collect enough data, you can use statistical analysis to determine the probability or probability of failure with your NDE information. So you can quantify it. It's just you have to do a lot of data analysis on it before you can quantify it. So when I say that you shouldn't take NDT data as a quantitative measure, what I mean is that you cannot take a reading somewhere and then just use that reading. You want to do a lot of analysis on it and only then take that value.
Yeah, so that means NDT methods are only indicative methods, we can say, because we cannot quantify. If we are talking about the health monitoring of structures, so we have
Again, it depends on what we're trying to quantify. So if you're trying to quantify stiffness, then I would suggest that we go for a destructive test, do the models of elasticity test versus doing ultrasonic pulse velocity. But if you're trying to find out if there's a crack in your system, NDT can be a good measure, a good way to do that. So it really depends on what your ultimate goal is.
Right. Thank you so much.
No problem. I will unmute Dr. Raghu Prasad. I think they're not available. So I'm going to do Suhas U.
Hello, good morning, madam.
Yes, sir. Yeah.
Madam, I'm good. Dr. Raghu Prasad speaking.
Yeah, please go ahead.
Yes, excellent session. Yeah, I think you called my name, na? That's what I.
Yes, sir. Yeah, I did.
Okay, good. Thank you, madam.
I think you had a question, sir, so that's why I asked. Okay, in that case, I'll move on to the next person, which is Saumitra Das. Sorry, I unmuted you by mistake. Yeah.
Hello.
Yes.
Thank you, ma'am, for this session. Actually, I'm from Bangladesh, and I'm going to start my PhD at University of Nebraska Lincoln soon. And my professor also works with breeze monitoring with Nebraska. I have two questions.
One second. You got cut off, so I couldn't hear anything you said before. So could you please repeat all that?
Okay. Actually, I'm going to start my PhD at University of Nebraska Lincoln, and my professor also works with the breeze monitoring with Nebraska Breeze Authority. I have two small questions. Like, between the destructive test and non-destructive test, which one is most widely used?
Destructive tests are definitely more widely used than NDT.
The world. And the second one is which softwares needed, which basic softwares works like in the structure.
Again, what kind of software you use will be dependent on what your data is like and what you're trying to do with it. So if you're trying to do a mathematical analysis, I would suggest going for something like MATLAB. But if you're going to do statistical analysis, you would want to go for something that's more focused on statistics like R or SPSS or something of that sort. Again, it's all very dependent on what your data is like and what you're going to do with your data. Does that answer your question?
Okay, thank you.
Yeah. I'll unmute the next person, that is Sachin Dyavapanar.
Can you hear, ma'am?
Yeah.
Really, it was a session, and I have one real life problem doubt, ma'am. In a building, suppose we are facing a crackage issues. in which type of method is suitable for the determination of cracking?
So if you're seeing cracking in a building, I think the most commonly used method is you just look at it visually to see it. And you can always use strain gauges to see how much the crack has increased over time. That is one of the most commonly used methods. So you will essentially fit a strain gauge over where the crack is, and you can come and look at it periodically to see how much the strain gauge has moved. So that is probably the easiest way to monitor a crack.
Okay. And as per advancement, I am asking about the advanced technologies, which is suitable.
If you have something visible, generally you'll just go for a visual inspection because that is the most reliable way. But if you're looking at cracking in concrete, yeah, that's probably it. You look at strain gauges. That's the. It's a very simple problem, so it has a very simple solution, right? Again, you can also do volumetric measurements to see if there's any shrinkage or expansion. But if your problem is visible cracking on concrete, it's just strain gauges. Because you can always try and use something like ultrasonic pulse velocity to see how much the velocity is changed and all that, but your results would be much more reliable if you just take strain measurements. Does that answer your question?
Okay, next question, madam.
Okay. Next one is Saumya Shri. I think she's not available. So I'll go with Baswaraj Salimani.
Hello, Dr. Savita. This is Saumya Shri.
Hi.
Yeah. I have a doubt about, not a doubt, I need a clarification about the results of this, all this NDT test, all this, how reliable that are. If I consider a dam structure, for that I need to conduct this structural monitoring, health monitoring test. Then in its complete lifespan of 100 years, how oftenly I can conduct it, and if I am conducting at once, that is okay for that, complete lifespan of that dam?
No, not at all. So to answer that question, NDT needs to be done at regular intervals like any other maintenance system.
Okay.
And especially for things like dams, you have to do it. I'm not sure what the frequency is, but how many ever times it needs to be done, it has to be, regularly done.
Okay, right. Thank you.
It's again, NDT is not a one-time thing. You have to continue to do it at periodical intervals or have a system that gives you continuous information.
Okay, well.
So yeah, the next person is Baswaraj.
Okay, Ramchandra.
I think that's not working. So I'm going to ask the last question to Mr. Ramachandra. I think we'll end with this. Is that okay, sir?
Yes, madam.
Okay. I don't think they're okay. Yeah.
Okay, any other questions from audience?
Hello.
Yeah, I think Mr. Ramachandra is asking a question, sir. Yeah.
Hello. Hello.
Yeah.
Hello.
I can hear you, sir.
Hello. I'm Ramchandra Niturkar. I'm the chairman of DSRB committee for the World Bank sponsored by in Maharashtra. I am for the technical audit of the big dam, major dams. My question is for the health monitoring of the old dams, especially in the masonry structures, which non-destructive testing is suitable for especially going for the voids in the due to the seepages, and for the substandard work in the dams, there are some voids. How to trace the seepage pass in the major dams and calculating the this voids in the dams.
So since you said it's a masonry structure, that kind of eliminates a lot of NDT methods that we can use, because masonry has multiple materials. So that, because of that non-homogeneous material, it's kind of hard to do NDT on things like that. But since you said one of the major concerns is voids, you can always use infrared thermography to see where seepage is, because obviously wherever you have leakage, it'll have a different temperature compared to the spots where you don't have any leakage.
That means you recommend thermography. Hello.
I think it might work. I've never done it.
What about the electromagnetic system which you explained, ma'am? Big noise is there. Hello.
One second.
Hello.
Yes, sir. Can you hear me now?
Yes, I can hear you, ma'am.
Yeah. So I've never really done infrared thermography on a dam, so I cannot say whether it'll work or not, but it is something that you can try. And you did ask me if you can do
magnetic.
I'm not sure what.
Electromagnetic. Hello.
I don't know. Again, I'm not sure which. Electromagnetic will not work because it's not a magnetic material, right? So magnetic particle testing can be used only on steel or iron and its alloys. So you cannot use it on anything that's not an iron alloy.
And what about this acoustic emissions, ma'am?
Acoustic emissions might be possible. But again, because there's a lot of water activity that would be happening behind your dam, that data can sort of, those sound waves or sound pieces that get detected will be a problem in your data. But if you can figure out a way to cancel that noise from the water out, you might be able to use it.
That means you say tomography is slightly reliable.
Thermography might be the best method for you to see where your voids are.
And what about the dye method? Putting the dye in the upstream, and then what about this dye method, color dye method?
Again, if you want to use ferro dye, it might, unless you want to use, I don't know how you would do that though.
Yes.
You can dye it with just a regular thing and see if it works. But again, I'm not sure what the logistics of that would be.
Okay, madam. Thank you very much. It's a good presentation, very knowledgeable. I'm thankful to you.
Thank you so much.
Madam, okay, can you hear me, madam?
Yes, sir. Yeah.
Okay, so fine. It was a good interaction session, and I request our participants, if you have any questions, please mail to that webinar.civil, which is in the brochure. Okay, so that madam can mail you. Fine. So we will wind up here only. So before winding up, I would like to thank Dr. Savita S. Srinivasan for a wonderful session. Okay, our participants have gained a lot of knowledge here now, and you have managed it very nicely. So I request all the participants. First of all, I would like to thank all the participants around the globe who have gained all the knowledge here now. So now I would like to conclude this. So Savita Srinivasan, if you want to speak few words, you can speak. And before that, the feedback forms will be sent to you through the mail or through the WhatsApp group, and it will be valid up to today evening, up to 4 p.m. Later, and tomorrow there will be again one session. Who will be our Brijesh Prithvirajan sir will be managing with that. Okay. So I would like to conclude here. And before concluding, as I told you, Savita Srinivasan, you can speak few words and you can wind up.
I hope everybody had fun and also got some information on structural health monitoring systems. And thank you so much for the opportunity. And Dr. Patil and I have been speaking for almost a week about this regularly. And he's been very helpful with helping me set this up because this was my first webinar. So I'm new to this whole thing. So thank you so much for, helping me out with everything. So thank you so much. And also Jain Institute for the opportunity.
Yeah, it's our pleasure. Okay, behalf of management, behalf of principal, I would like to thank you once again. Also, I would like to thank our coordinators, Bharat HM, Raghavendra HS, and Umesh HM for organizing this. And I think so I have disturbed you for last 1 week, okay, because of this particular session. So, and I really thank you for managing the time. I think so it's already now 2 or 2:30 AM there, but even though you are with us, thank you once again.
No problem. Thank you so much.
Okay. So thank you, Savita. So we'll see you tomorrow again. And I like to inform the participants, join once again tomorrow morning, same timing. It will be around 10:15. So 10:30 the session will be starting. So it will be this, the particular topic will be concepts of concrete. So till then, have a good day. See you. Bye bye.